Anyway, on Sunday, the third day of my story, I started drawing out some things on paper on my kitchen counter. Here's my first page of notes that are directly in keeping with my goal to truly embarrass myself. I wanted to put every mystery I'm aware of on one sheet of paper and try to sort them all out. So I have an illustration of the sprawling bush of evolution alongside the punctuated equilibrium model that shows species just emerging more or less fully formed. I've written notes about protein folding and how there are 10 to the 22nd different options and hundreds of thousands of minimum energy states in protein that a plant can somehow determine whether it will become a cabbage leaf or a palm tree. I've also written a little thing about stem cells that when divided up into 16 cells can become either a heart or a liver. That's over here. I boxed in a drawing of the inflationary model of the universe down here, a fuzzy remnant of the cosmic microwave background, or CMB. I circled dark matter and dark energy with the word Higgs at the bottom down here, referring to the Higgs boson. That's the God particle. In the center, I've written energy and matter with a big circle that ties it all together with the word form and the work of Rupert Sheldrake, morphic fields and morphic resonance. And I came back later with the black pen and wrote 100th monkey somewhere here, 100th monkey, to the side, and some notes on unique and unusual features of the theory of morphic fields and morphic resonance. I've written a note about flocks of birds and schools of fish, how they resemble a magnetic field that they're being influenced by. Joint attention studies in monkeys and child development, and how the effective fields don't fall off at distances and are not distant dependent. And that there's quantum entanglement going on, or, what I've written up here, spooky action. So that was my first draft. Now here's my second page of notes. I started by drawing out a diagram of the inflationary theory of the universe, so it inflates right down here, and then decided it was important to include a couple scientific aphorisms that I found in a Google search and talked about on the radio show a while back. The first is this one, and obviously I'll need to read it to you. The grand aim of all science is to cover the greatest number of empirical facts by logical deduction from the smallest number of hypotheses or axioms. Albert Einstein. So in other words, somehow I have to whittle down all the mysteries from my first draft and make sure that I'm not extending it too far. The second quotation refers to some thoughts on how morphic fields could work non-locally, although this is more about magnetism, electromagnetism. It says, "This is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there." Heinrich Hertz, you know, the megahertz, gigahertz frequency guy. So I'm going to come back to that later, thinking that morphic fields and morphic resonance are the things that we cannot see with the naked eye, but they're there. So anyway, the diagram on the left is a model of the inflationary theory of the universe with a circle referring, this circle right here, referring to the leftover heat of the Big Bang known as the CMB, where I've written highly and underlined organized. Outside the diagram, I've started to write atoms with a diagram of the periodic table, and then molecules, then protein folding here, and then cells, and then the diagram of punctuated equilibrium of evolution right here. I've started to write equilibrium also down here with a line drawing from the Big Bang to the end of the universe. And finally, I've got some PENROSE, what I call entropy boxes, that will show up later. And on the right, I've written down the words attributed to morphic fields, trying to get that clear in my mind. Memory and habit, across filaments, resonating. Don't worry, I wasn't sure where this was going either, but just trying to get everything down on one sheet of paper. Well, this is the book I was looking into, Cycles of Time by Roger Penrose, copyright 2010, Vantage, New York. Thank you for writing this book, Dr. Penrose. It is quite a black diamond in terms of ski slope difficulty. My Sunday began trying to look back at the drawing Penrose made depicting two types of entropy, gas in a box versus gravitating bodies. And entropy for gas in a box, you have this small box right here, and then these little doors open up, and entropy and time go this way with it spreading out and looking all uniform. Well, for gravitating bodies, we have all these gravitating bodies all separated like this, and then with gravity, they start to clump together and clump together even more until we're left with part of a clump over here and maybe one black hole over here. Well, here's the interesting part. So for entropy over time, gas in a box versus gravitating bodies, these two look the same. What's entropy for one thing is almost the opposite of the other, but they're identical. So they look the same, which makes you wonder why. Then, just as I reminded myself I didn't really understand this oddly special nature of the Big Bang, which was the title of this chapter of the book, I flipped back a couple pages to this diagram on page 71. Now under here it says figure 2.6. It says frequency spectrum of the CMB as initially observed by COBE, the space telescope, but supplemented later by more precise observations. Note that the error bars, you can see them easier here, are exaggerated by a factor of 500. This shows precise agreement with the Planck spectrum. In the text above, it describes the continuous line, this continuous line, sorry, I lost my place, as Planck's black-body curve, which is given by the specific formula, and it is what quantum mechanics tells us is the radiation spectrum of thermal equilibrium for any particular temperature T. So we already have thermal equilibrium in the cosmic microwave background, which is 360,000 years before the Big Bang supposedly happened and everything inflated after that. So at the time 360,000 years before that, or after the Big Bang, it was already in maximum entropy, that is, dense and hot. It was all thermal equilibrium. Now, how could something already in a state of maximum entropy, I repeat, already, continue along a course of increasing entropy? It doesn't make sense. Now, in Penrose's extraordinary view of the universe, he describes universes that occur in a succession, each of which he calls an eon. The end of the universe and maximum entropy of gravitational bodies puts thermal equilibrium after a succession of final pops, these little pops of singularities and black holes that apparently put the universe in the same state as the qualities we use to describe what gave rise to the Big Bang in the first place. That is the oddly special nature of the Big Bang. So anyway, I started to draw this, my third draft, which after I end up adding a few more things to it, ends up being the final version. Now, I will come back to this one in a moment, because as I started to draw out this model, it spurred some questions I wanted to answer before I finished it. It's now Monday, day 4. I know that because this next scan actually has a date and timestamp of Monday, February 18th at 3:53 p.m. Central Standard Time. It was President's Day and I had the day off. Well, this is a printout from NASA. It describes, I'm not going to be able to pronounce it, the WMAP, a pixelized illustration of the cosmic microwave background without the interference of the Milky Way and other galaxies, all the way back to measuring what would have been the hot ionized gas at the time that is measurable now only as low-frequency microwaves, the leftovers of the Big Bang. I look at how uneven and clumpy the WMAP is, and I start to do some Google searches, why is it clumpy, and I underline the explanation for why the perfect thermal equilibrium looks this way. The early expansion and clumpy nature of the diagram is due to something I don't quite understand, which it says, tiny fluctuations were generated during this expansion that eventually grew to form galaxies. Okay, tiny fluctuations, what does that mean? The WMAP science team, they congratulate themselves here by saying the WMAP's precision measurement of the properties of all the fluctuations have confirmed specific predictions of the simplest version of inflation. And it goes on to describe how the fluctuations follow a bell curve, which I drew at the bottom. My only handwritten note on this page says, "See Dr. Spergel." So who is Dr. Spergel?